RC and RL circuits made easy. RC and RL circuits can be modeled by differential equations. And for our example, we'll use an RC circuit. And we have it drawn here, and we have the currents going through the capacitance defined by this relationship, and the current through the resistor defined by this relationship. We can use KCL to try to solve for the voltage and time, and we get the capacitor voltage plus the resistor voltage equals 0. Why is it positive and equal to 0? Because these are both going in the opposite direction, and I happen to be using the positive current direction with derivative direction definition of a capacitance current voltage relationship. So once you get this relationship, you can use a variety of techniques from your differential equations to come up with the voltage and time, which you can see starts at a exponential when t equals 0, starts at v0 when t equals 0, and exponentially decays to 0. Now, it's true, if you do this enough, you can look at this and just write it without a lot of separation of variables or things like that. We will go over maybe a more easy to use technique called the Laplace transform at the end of the talk. Now, LTspice can do transient simulations of this circuit, and you don't have to actually solve for the function in time. And you see I have my parameter values where I'm programming the initial condition 1 volt, the capacitance and the resistor, and tau, something we'll see what it does later, is simply R1 times C1. Because I only want the simulation to go to 5 times tau. So if I change C1 or R1, the simulation will automatically go the proper amount of time. How does this occur? .tran is the variable stop time. Something else we need is an initial condition, .ic, v of t equals v0. Now this isn't really time, it's really the node voltage, but it looks like v of t. Again, you can download this file and run it. And here would be the transient response. Starts off at 1 volt and goes very close to 0 volts in 50 milliseconds. And we can even plot this in terms of tau by left-clicking on the x-axis and just dividing the time by 1k by 10u. And you can see 1, 2, 3, all the way out to 5 tau. Now there's some 5 tau is an important number because you're almost decayed to 0 by 5 tau compared to your initial starting condition. So something you need to know in any exponential circuit like this, after more than 5 tau, essentially a capacitor is discharged all its voltage. Another important time is 0.69 tau, which will give you half your initial condition. And another one is 1 tau, where it gives you 38% of your initial condition. So effectively, 0.69 tau, 1 tau, and 5 tau are things you need to keep in your memory so you can talk about how fast things will rise or fall in a capacitor or inductor-like system. You can even solve for this numerically using Excel, using Euler's method. And you can download this file, and you can look at the plot, it's already there. And it's really V new, which would be like at time step 1, would be the old V out, which in this case was the initial condition, 1 volt, plus H times 1 minus R1 C1 times V old. And if you just, again, you can see how I programmed it by downloading that file. Now I'd like to talk about using the Laplace transform, where we can turn calculus into algebra because we're turning time into frequency. And some operations in time that involve calculus can involve simple algebra when we convert to frequency. And so if we look at the derivative of the capacitor voltage with respect to time and transform that into frequency, we have dV dt, and here we have SVS. And of course, this C1 is just a scale factor. And the easy way to remember that is as change goes up, frequency goes up, because a derivative is change, and frequency you can think of as change as well. So the derivative is linearly related to frequency, and that's we have this S. Here we'll use T, and the frequency domain we'll use S, and you need an initial condition to start. So now we can rewrite these equations into the Laplace transform, but now rather than having to find a differential equation solution by kind of guessing at a form of VT and then solve and check your guesses to see if this we solve that differential equation. Now we just have to solve algebraically for VS, which has a form similar to this, and then we can look up the inverse and go back into time by just looking at a table. And we get Vt equals V naught e to the minus t divided by 12. And eventually, yes, once you see this form, you will just remember that the inverse transform of that back into time is this relationship. So a capacitor can be transformed into a frequency-dependent device that can be analyzed with any technique we've used before. Again, here's the time-dependent voltage current with capacitor, and here we are in the frequency domain. And if I solve for voltage, I get two things. I get the initial condition divided by the frequency plus the current in frequency divided by SC1. Now if I look at this, this looks very much 1 over SC1 like a resistor. And so I've called it Z for impedance, but I can have 1 over SC as a resistor, and I can have this voltage source VO over S. And with that, I can, rather set up a differential equation in Laplace transform, I can take the Laplace transform of every capacitor and then use all our other analysis techniques to come up with an answer. So we can go back to solve our RC circuit. Instead of R, I'm calling this Z. So I have Vs, and the current through this capacitive node is Vs minus V naught over S. Simple. This voltage minus that voltage, divided by the resistance, or the effective resistance. IR1 is the same thing. If I rearrange this, I get IC1 equals SC times the difference in these two voltages. Then I can apply my KCL, solve for Vs, and do an inverse lookup. Now it might seem that it was extra work at this point, but when we start doing more complex analysis and more complex circuits, you'll see that taking a regular circuit, RC, and transforming it into the frequency domain will allow us to do all kinds of analysis in the frequency domain that we used to just be able to do in the DC domain. Now RL circuits or any other system of linear differential equations can be analyzed in the same manner. And the thing is once we transform a circuit with our resistors, capacitors, and inductors into the frequency domain, we can use all of our analysis tools we've covered so far, such as Ohm's law, Norton and Thevenin equivalence, source transformation, voltage division, current division, resistive equivalence, capacitive equivalence, inductor equivalence, superposition, nodal, mesh analysis, and op amps. I've been told that A lot of other majors, they might not use resistors, capacitors, and inductors. It might be mass, spring, and a damping factor, or things to do with heat transfer. But this technique is pretty powerful. I suggest you learn it.